All right, shall we start? Um, Now we have in the previous lecture we have some discussion on how to generalize our formula sum in a full vector form, so that we can handle more complicated problems of about angular momentum and torque. And in particular, we have already shown that the Newton's second law for rotation in terms of the angular momentum is valid even for a system with a non-rigid body, even for a system with arbitrary motion of particles. The second law of rotation is still valid. We have already proven it. Now, so this is a most general form. The form torque equal to dl dt is the most general form of the equation. So in a certain application, we are not interested in that very general form, but we are interested in a situation where the axis of rotation is fixed, but the moment of inertia does change with time. And in that case, L is reduced to I omega, where I is the moment of inertia about a certain axis, and omega is the angular velocity about that axis. Okay, so this is a simplified form of the most general form of the Newton's second law of rotation. So this is a particular case. But even for this particular case, you have allowed the moment of inertia to change. Okay, so this still applies to a non-rigid body. Okay, so the only assumption is that the particle they interact with each other, but with a force that obey Newton's third law. Okay, if the internal force between the particle obey Newton's third law, and the line of actions of the force is along the line of action joining the particles, then we can apply this law. Okay. Now we discuss about another interesting phenomenon which we haven't addressed yet, and that is the translational and rotational kinetic energy. Now, in our previous discussion of motion of a rigid body, we say that in order to let you remember what we have said, I just share this slide in case you forgot. We said that the total kinetic energy of a body can be decomposed into two parts. The first part is the translational kinetic energy associated with the center of mass. So the center of mass is just like a point mass. Okay, you imagine all the mass of the body to be concentrated at that point, that is center of mass. And if that center of mass with the velocity big V, then the translational kinetic energy is half m big V squared. Okay, so that represents the translational KE. The other form of kinetic energy is the rotation. Okay, if you measure everything about the center of mass, if you measure the moment inertia about center of mass, and you measure the angular velocity about center of mass, then the rotational kinetic energy associated with that is half ICM omega squared. Okay, so the total kinetic energy is the sum of the two terms. Okay, now, but this is not generally this is generally correct as long as you measure everything relative to the center of mass. If you measure the velocity relative to the center of mass, and you measure the angular momentum and moment inertia relative to the center of mass, the kinetic energy can be separated into this nice form. Okay, so that is the main idea. For any other point, you cannot do this. If you choose another point and follow its motion, you will find that this relation will not hold. This relation holds only if you measure everything relative to the center of mass. And for this particular relation to hold, the energy can be separated into two terms, one for the translational motion and the other term for the rotational motion. Okay, now we are going to prove this formula for a specific situation now. What specific situation? We are going to prove this formula for a symmetrically rotating body. A cylinder, it may be a sphere, or it may be a hollow shell, hollow spherical shell. As long as it is circular, it's symmetrical about its rotational axis, that's okay. Now, this is a particular form of the most general formula, but I don't want to confuse you with the difficult mathematics, so I only prove it for this particular form. Now, suppose the cylinder is rolling and also moving forward. Okay. Now, I can always, if I take the rotational axis, this is the rotation axis, and I look at two particles on the opposite side of the rotation axis. Okay, these two particles are at equal distance, but at the opposite sides of the rotation axis. So they move with equal but opposite velocity. Okay, due to the rotation, the particle M, I consider only rotation here in this figure. So in the rotational motion, the particle M here moves with the velocity v, while on the opposite side, this particle moves with a negative velocity, negative v. So they have the same speed, but with opposite direction velocity. Okay. But I only have considered the rotational motion here. The object may still have a translational motion. So I assume that the translational motion of the center of mass is capital V, which is also a vector. Okay. So what is the total velocity of these two particles relative to the ground? Okay, you simply add up these two velocity, right? We form vector sum of the small v and the big V. And it goes like this. Okay, when we learn about vector addition, we use the parallelogram method to add the two vectors. So the gray arrow represents the sum of the two vectors, which is the total velocity of this mass relative to the ground. And we can also do the same thing for the particle on the other side. Okay, the particle here moves with velocity minus v. So when we add it to big V, it becomes this vector. Now from this diagram, you can't notice any similarity between these two arrows. They seem to be very different. Okay, but if I consider the kinetic energy of these two particles in a pair, I will have some mysterious result coming out. I will have some interesting result coming out. Believe me or not, let me consider it. Now, so I consider now the total kinetic energy of these two particles. So for the first particle, I have half m big V plus small v square. Now by square, what I mean is the dot product of a vector with itself. So it's the square of the absolute magnitude of that vector. Okay. And for the other particle, the rotational speed becomes minus v. So the kinetic energy becomes half m big V minus small v square. Again, by square, I mean forming a dot product of this vector with itself. Okay, so now I can expand this bracket. Okay, I form a dot product of the vector inside bracket with itself. So I have three terms: big V square, small v square, and also a dot product between the big V and small v. But I have two such terms. So I have two big V dot small v. Okay, so that is the case. And how about the second bracket? For the second bracket, I also have big V square plus small v square. But then I also have the cross term, which is 2 times the big V dot small v, but now with a minus sign, right? So these two terms will cancel each other, right? These two terms will cancel. And that what is left is 2 times of half m small v square plus 2 times of half m big V square. Can you see that? Now the miraculous thing that happens is that the cross term that involves the dot product between the big V and the small v, they cancel. So the energy you can see seems to be separate. this seems to be, the first term seems to be the rotational energy of the two masses. Okay, I simply count the rotational velocity without involving the translational motion. And if I calculate half mv squared multiplied by 2, I simply got the energy, the rotational energy of that. And the second term is about the translational energy. I simply treat them as point mass moving forward with velocity big V, and I calculate half m big V squared multiplied by 2. I got the translational kinetic energy. So if I consider the pair of particles on opposite side of the body, the cross term vanish, and I can separate the translational kinetic energy with the rotational kinetic energy nicely without the cross term. Okay. So what I'm going to do next, I think you know. Since this is a pair only, right? This is only a pair. I can sum up all pair that contribute to the whole body, right? For each pair, I have this sum, but I can sum up the kinetic energy from all opposite pair, and it becomes the kinetic energy of the whole moving object. Okay, so for each pair, I have this separation. And so for the whole thing, I also have this separation. Okay, and also I would like to, instead of writing as m small v squared for the rotational thing, I write v as r omega instead. So it becomes m r squared omega squared for the first term. Okay, and when I form a summation, the summation goes to what? Goes to summation mi/ri squared, right? And that's become the moment of inertia of the body about the axis of rotation. And omega squared can be taken out. So the first term becomes half I omega squared. Okay. And the second term, if I form a sum of all the small m, it becomes the total mass, right? So it becomes half big M v squared, where v is the center of mass velocity. Okay. And that becomes the translational kinetic energy. So I've proven this. Okay. Now, I emphasize that this is only a restricted version of the most general formula that I stated earlier. Now the body applies to, now the proof applies only to a body which is symmetrical above, totally symmetrical above the axis of rotation. And in fact, for body without this symmetry, I can still prove this formula, but I will not let you know how to prove it because it's more difficult. And I don't want you to drill into the difficult mathematics without understanding the physics. Okay. Now, so this is the most general formula. Even for arbitrary body, you can separate the energy, the kinetic energy, into these two terms. Okay. This is for arbitrary, even not symmetrical object. You can do this, and we skip the proof for this case. Okay. Now, there might be some confusion in stating the energy of a rotating object. When we start our discussion on rotation at the very beginning, okay, we have proven that when a rigid body is undergoing a rotation about a fixed axis, which I call O, with the angular velocity omega, then the kinetic energy is half I omega squared. Right now, this is what I've proven at the beginning of this chapter. Okay, so there's no translational motion. Okay, it's a purely a rotational motion about a certain axis, about the axis O, and the axis O can be arbitrary. Okay, the only you can pivot the object at any other point. As long as you are calculating the omega about that rotational axis, it is correct to state that the energy is half I omega squared. So that consists of a purely rotational kinetic energy. But if you consider a body with both translational motion and rotational motion, then you have to make everything reference to the center of mass. If you want to calculate its total kinetic energy, then you have to reference to the center of mass, and you should find the angular velocity about the center of mass and also the translational velocity, linear velocity of the center of mass. And the kinetic energy can be separated into two terms, the rotational part and the kinetic and the translational part. Okay, this is just what we have proven. Okay. Now it's important to let you know that if you have a body which is rotating about a fixed axis, just like this, okay, it is not correct to represent the rotational energy by half mv squared. It's not correct to use this formula. Okay, now because this is not the center of mass. Okay, this is the rotation axis. Now this formula, if you insist on applying this, you can still do it. But not only with this term, you still have to add another term. The moment of inertia about center of mass, you have to know, and also you have to know the angular velocity about the center of mass. This angular velocity omega is just the angular velocity about the fixed point O. So you have to do some mathematics to translate the angular velocity about O to the angular velocity about the center of mass. And you add that additional term, and if you are able to find the translational velocity also of the center of mass, the formula would be correct. But that is not suggested, because for a body rotating about a fixed axis, you can simply use this result, right? You can simply use half I omega square. Okay, you don't need to use this. You don't need to use this formula. Okay, so I don't suggest you to write this into two terms, if that is a rotation about a fixed axis. Okay. Now, if you want to know a very detailed discussion on the vector formulation for rotational dynamic, I recommend you to read this e-learning module. This is a really good explanation of all the rotational dynamics of a rigid body with the vector formalism. Okay, so but I will not go into the details here. So we end this chapter. And so we are going to start a new chapter on gravitation and planetary motion. Now this is very interesting. We have at the space age, right? So there are quite a lot of phenomena related to space travel, and also the satellite rotating about the Earth. And now we have the James Webb Telescope. It rotates together with the Earth around the sun. Okay, and it's kept at the so-called Lagrangian point, where it is rotating together with the Earth with a common angular velocity around the sun with the common angular velocity as the Earth. So this is a very interesting phenomena. And we also have discussed some exoplanet. The exoplanet are planetary system outside the solar system. So that also relies on orbital motion. And orbital motion, we rely on the Newton's law of universal gravitation and the law of motion to describe that. And we are going to do some of this description in this chapter. Now, so what is Newton's second law? Newton's law of universal gravitation. Now, Newton's law of universal gravitation states that two Mond masses, they attract each other with a force proportional to the product of their masses and inversely proportional to the square of the distance. Okay, so it applies exactly to 2 point masses. So if you have by point mass, I mean the size of the mass is small compared with the distance. So if you have two very small masses, big M and small m, and they're separated by a distance r, small r, then the gravitational force is exactly GMM over r squared. Now, this form of the force law is also called the inverse square law force. By inverse square law force, I mean the force is inversely proportional to the square of the distance. Now, many forces in nature are inverse square law force. For example, the gravitational force, and also for two static charge, they attract and repel each other by the Coulomb's law. Coulomb's law also state that the attraction force or repulsive force between 2 point charges is inversely proportional to the square of the distance. Okay, so there are quite a number of laws force law which obeyed the inverse square law form. Okay, and the proportionality constant G is known as a gravitational constant, and it takes on such a value and units in SI unit. Okay, now but you should be careful about this law. In fact, the law in its original form is only valid for point masses. If you want to find the forces between 2 extended bodies, you have to do an integration. And the integration is in general very difficult to do. Now let me explain to you why. And suppose you have 2 extended bodies like this. Or maybe not so complicated. Let me imagine you have an extended body with a continuous mass distribution, extracting a point mass here. This point mass is small m. And this is the big M. Sorry, the point has gone. Now, if you consider a small pieces of mass here, which I call maybe delta M, the delta M will have a distance R from the point mass. Okay, so it's correct to say they attract each other with such a force, delta big M, small m, over R squared. Right? That is correct. But the R will not be the same at a different point. If you consider the small pieces of mass here, the R will not be the same. Right? The R will change as I move along this object. Okay, so you don't know what R you should take. And also the direction of the force will change. You have to add the direction of, you have to add the forces between these 2 pieces of mass and these 2 pieces of mass by using the vectors. So you don't know what will be the result after you add up all the contribution from these small pieces of mass. Okay, so in general, you will find that the inverse square law force of this form will not hold for extended body. You cannot simply apply this form to a extended body attracting a point mass, or even the attraction force between 2 extended body. You cannot simply apply this. If you really want to calculate the attraction force between these 2 bodies, you have to do an integration. You have to divide this object into many, many small pieces, and you add up the forces between each of the pieces with the small m, and that sum will eventually become an integration when my pieces of mass is getting very small. Okay, so you have to do an integration. Now, but there is a special case. The special case is found by Newton. Newton found that we have a special case. If you have 2 spherical mass distribution, what I mean by 2 spherical mass distribution is this. I'm not drawing very well, but let me assume that this is spherical and this is also spherical. If I have 2 spherical mass distribution, the mass are symmetrically distributed about the center. And also for this one, then the attraction force between them is exactly given by GMM over R squared. As long as the R I choose is the distance between the center of the sphere. If I choose R to be the distance between the center of the sphere, then the gravitational force is exactly given by GMM over R squared. But that requires integration. And Newton, he actually did an integration to show that for this particular case of a 2 spherical mass distribution, the force is exactly GMM over R squared. So that is only for this case only. Okay. And we are also interested in writing the law in a vector form. what is the vector form? We write the direction, right? The magnitude is already given in the previous slide. Now we are interested in the direction. Now, how do we specify a direction? Suppose I have the sun attracting a planet. Okay, the planet is moving, the sun is stationary. So the planet is being attracted towards the sun, right? And I place now the sun at the center of a coordinate system. Okay, so the position vector of the planets is given by the vector r. Okay, this is the common position vector. It points from the origin of the coordinate x coordinates to the planets. Okay, so this is r. And you can also express it in terms of the component. In the Cartesian coordinate, the component of r is xy, the coordinates of the planets. Okay. Now, how do we specify a direction? The direction of the attraction force is towards the sun. Okay, so this is in the opposite direction to r. Okay, so I use a unit vector. A unit vector r hat is defined by the vector r, the position vector, divided by its length. So this is a unit vector without carrying any magnitude. The magnitude of this vector is 1. Okay, and I deliberately add a minus sign here to specify that the direction of the force is opposite to the position vector. The position vector is pointing outwards from the sun to the planets, while the attraction force, the gravitational force, is attracting the planet towards the sun. So it has a direction minus r hat. So by adding the vector minus r hat to the equation, I can fully specify the position, the direction and the magnitude of the gravitational force. Now, but I can also express the r hat vector in terms of its Cartesian component. We know that the r vector can be written as xi plus yj. Now I express the r vector in terms of its Cartesian basis, I and j. So it becomes xi and yj. While the magnitude of the r vector, which is small r, is given by Pythagoras theorem as x squared plus y squared square root. So the r hat vector is actually xi plus yj divided by the square root of x squared plus y squared. Now you should notice that x, y, they are changing with the position of the planets. If the planet moves to another position, the x and the y will change. Okay, so the r hat vector is not a constant vector. It is changing with position. Okay, it is changing with position. If I move to another position, then the r hat vector will change. And it's apparent from this figure because the direction of the gravitational force will change with the position of the planet, right? And also the magnitude of the force. If the distance between, if the planet is now not in circular motion, but in the elliptic orbit, say for example, the r and r change, the magnitude of the gravitational force will also change. So none of these are constant. If you consider a very general motion of an elliptical orbit, the r hat is not a constant. The small r is also not a constant. They are changing with x and y as the planet move along around the sun. Okay. Now this is a 2D formula sum, but you can generalize to 3 dimensions if necessary, but that is usually not necessary because in most of the situation we study about the gravitational force between 2 objects which lies on the plane. So the motion lies on the plane, we don't need to generalize it to 3D. But if you are considered the motion of James Webb telescope about the Lagrangian point, then you actually have to generalize to 3D because the James Webb telescope actually is not stationary at the Lagrangian point L2. It is moving vertically in a small circle. And in those cases, you have to generalize the formula sum to 3 dimensions. And if you are studying a motion of a comet with a high angle of inclination relative to the Earth orbit, then you probably have to generalize to 3 dimensions. Okay. Now we take the x component and the y component of this equation. Okay, so the x component is given by minus GMM over R cubed multiplied by x. Okay, and the y component is given minus GMM over R cubed multiplied by y. Okay, the y, the x over R and the y over R here comes from the resolution of component. In fact, the x over R is a cosine theta. The y over R is a sine theta, so to speak, if you express everything in terms of this angle. Okay, and R is x squared plus y squared square root. Now you should notice that the gravitational force has such a property. It is universal, and that means any object with masses, with mass, will exert a force on another object with masses. So any object with masses will interact with each other through the gravitational, through the universal gravitational force. And the force is mutual. It means that the force exerted on the two bodies are equal and opposite. Okay, so they form an action-reaction pair. Okay. So the sun attracts the planets by a force F, but at the same time, the planet also attracts the sun by the same force. And the two forces are in fact in the opposite direction. Now we usually omit the force acting on the sun because the sun is so massive, the mass is so large that under the action of this force, the sun is almost motionless. The force is too small to move the sun by a large amount. So we usually neglect the force acting on the sun in this diagram, and we assume the sun to be stationary at the coordinate center. So this assumption is based on the fact that the sun is too massive compared with the planet. Okay. Now, in the 19th century, an English experimentalist, Cavendish, he did an ingenious experiment to find out the value of the gravitational constant G. Now, why is this necessary? Why is it necessary to find the gravitational constant G with a laboratory scale experiment? Can I measure the value of G by using the motion of planets, by observing the motion of planets around the sun in our solar system? Or can I observe the find the value of G by observing the motion of the moon around the Earth? Well, that is not possible. Why? Because when you study the gravitational force of this form, GMM over R squared, the G always comes with the M. The M is the gravitational center, and in this situation, the M is the mass of the sun. But we actually don't know the mass of the sun, right? Its gravitational effect is the only way for us to measure its mass. But that mass is unknown, and that mass always comes with the G. So we cannot distinguish whether the effect is from the G or from the mass M. We cannot distinguish the two objects in the observation. They always come together. Okay, so you can measure the combination GM, but you cannot measure G and M individually because they always come together. And similar things happen to the Earth. When you observe the moon moving around the Earth, or you observe a satellite, a small satellite moving around the Earth, what you can observe is the combination GM, where M is the mass of the Earth. But there's no other way for you to measure the mass of the Earth, right? So when GM comes together, you cannot distinguish what is the value of G and what is the value of M. You cannot find it. So the only way at Cavendish time to find the mass of the Earth and the mass of the sun is to perform a separate experiment to measure the value of G. If that is possible, then you can use the known value of G to determine the mass of the sun and the mass of the Earth by its gravitational effect on its surrounding body. Okay, so that is his idea. Now the experiment is ingenious. Okay, it consists of two pairs of mass. This pair I call it big M. Two masses here to the end of a beam. The beam is pivoted here, and there is another pair of mass which of small m, and is suspended by a fine fiber. You use a fine fiber, just like a fishing line, Okay, maybe it's narrower than a fishing line, but very fine fiber to suspend two masses, two small masses hanging on it. Okay, so it balances at the center. Okay. Now, so you can see the big M and the small m on this side because they are placed very close together. They attract each other. Okay, so the beam, the rod here will be twisted. Will be twisted by the gravitational force because the gravitational force produces a torque to twist the fiber. But the fiber, when it's twisted, it produces a small restoring torque. The fiber is somewhat like a spring. When you try to twist it, it will have a restoring force due to its material that tries to produce an opposite twisting force to oppose that. Okay, so by measuring the twist of this fiber and knowing its material property and also its dimension, you can calculate the gravitational force between these two bodies. Okay, and typically in this experiment, we have a small m and a big M of the order 1 kg, and the separation is of the order of 10 cm. Okay, but this is a very laboratory scale experiment. And if you plug in this number into this formula with the current known value of G, then you will find that the gravitational force is as small as 10 to the power minus 8 Newton, which is extremely small. 10 to the power minus 8 is 100 million, 1 in a 100 million Newton, which is extremely small force. But with a very thin fiber, with a very long and thin fiber, you can still produce a small torque to just counterbalance the torque produced by the force of gravity. And so you will be able to measure the gravitational force. Okay. Now, a modern version, not a Cavendish time, but a modern version of this experiment consists of a light source, typically a laser source, and there's a mirror here. The mirror reflects the laser light on the scale. So when the fiber twists a little bit, the reflection of the mirror will turn, and the angle of turn will be recorded on the scale by the reflected laser beam. That is how you measure the twist to a high accuracy. Okay. I have already emphasized this situation. If two masses are spherical, with mass M1 and M2, if they are spherical, then the force is exactly 1/r². Without any correction, as long as the R is taken as a distance between the center. And that is Newton's achievement. Newton actually used integral calculus to analyze the gravitational effect on extended body based on a law which apply only to the point mass. So starting from a point mass formula, he integrates all the point mass pair contribution, and eventually he find that for a spherical distribution, the 1/r² formula still hold, as long as the R is taken at the distance between the center of the sphere. Okay, so that is a success of integration calculus. Now, for this course, I don't want to confuse you with the difficult mathematics, so I skip the general proof. I will not let you see the general proof. But I just want to discuss with you some of the important consequence of this law. With this law, we are able to calculate the gravitational force of any spherical body, and as a result, we can understand the motion of the planet around the sun and the motion of the satellite and motion of the moon around the Earth. All this kind of phenomena can be understood by using this special situation. Now let's discuss about the gravitational potential. Now this is just a sort of review because we already have discussed gravitational potential energy when in the chapter of work and energy. Okay, now we introduce the idea of gravitational potential, which is essentially the same as gravitational potential energy. It's just different by the mass of the body. Okay. Now, so assuming 2-point masses at distance r, this is a gravitational force. And what is a gravitational potential? It is the work done by external force in bringing a unit mass from infinity to the present position. Okay, so you imagine now the small m is now a mass of a unit value. Okay, it is in SI unit, it may be a 1 kilogram mass. Okay, so it is called a unit mass. So I assume that now I have a unit mass placed at a certain distance from the large mass m, and now I move the unit mass from infinity to its final position r, and I calculate the work done by the external force in doing so. Okay. Now I think you know the answer already because we have already done it in chapter 5. Now I divide the gravitational force with the mass m to get the mass per unit, to get the force per unit mass. Or essentially, I can assume simply the mass m is 1. Okay, we get the same result. Okay, so the work done by the external force is integrating this f over m from infinity to r, but I have to add a minus sign because the external force is opposite direction to the gravitational force. So I've added minus sign to denote that I'm referring to the work done by the external force, not by the gravitational mass itself, but not by the gravitational force itself. Okay, so if you let me write down. So this is the gravitational force, and in my mind, I have this one. The external force being equal to minus F. And what I'm calculating here is the integration of the external force over the distance from infinity to R per unit mass. Okay, so this is what I calculate here. Okay, so if I put it back, it becomes minus F, and the minus sign will go on because there's an additional minus sign here. So I'm integrating gm over small r squared from infinity to small r. And that gives me gm multiplied by minus 1 over r, evaluate r at the upper limit and infinity at the lower limit. Okay, the lower limit term is 0, and the upper limit term will give me minus g big M over r. And that is the so-called gravitational potential. Okay. Again, a word of warning, don't just multiply the force by the final position R to get the potential. It's not correct. You have to rely on integration, okay? So this is the gravitational potential. Now I'm calculating the work done per unit mass, right? So if I calculate the work done for a body of mass m, right? The value will be what? Will be the gravitational potential energy, U, that we learned in chapter 5, right? So this is in summary, the gravitational potential energy and the gravitational potential, they are just different by effect of small m. Okay, for a body of mass small m, the gravitational potential energy is small m multiplied by the gravitational potential V. Okay. Now, why do we define a gravitational potential V? Because we don't want to rely on the property of this small mass m. We want to have a potential function that only depends on the gravitational center, the mass of the gravitational center, big M. So it is solely the property of that gravitational center. So we define the gravitational potential of the big M as minus gm over r. Okay, but it's nothing, but it's just different from the gravitational potential energy between two mass by only a factor of m. Okay. Now we can define another quantity now, which we call the gravitational field strength. What we call the gravitational field strength is the gravitational force per unit mass. So it's F divided by M. And I denote this gravitational field strength by the symbol G. But I know that the gravitational force can be written as the spatial derivative of the potential energy, du dr, with a minus sign. Now this we learned in chapter 5, right? In chapter 5, we learned that the force is negative the derivative, the spatial derivative of the potential energy. Okay. But since the U, the gravitational potential energy divided by M, is the gravitational potential, so the field strength G is just minus the spatial derivative of the gravitational potential. So G is minus dV dr. Okay. Now you may wonder why I call the gravitational field strength G. Okay. Now, by Newton's second law, the acceleration due to gravity at this point, if I suppose I'm an apple at a distance r from the center of the Earth, the gravitational force between them is gmm over r squared, right? So if I want to find the acceleration, it would be F over m, right? F over m is exactly minus gm over r squared, which is the gravitational field strength G. Okay, so that means the gravitational field strength G is just the acceleration due to gravity. It's just the acceleration here at this point due to the force of gravity. Okay, so A and G are actually the same thing. So that's why I use the symbol G, because I usually use the symbol G to denote the acceleration due to gravity at a certain point in space. So I won't introduce another symbol, but I just want to use this symbol G to denote the gravitational field strength, because it's the same thing as the acceleration due to gravity. Okay. So this is the whole thing. So let's have a summary. What he have introduced in chapter 5. We have introduced the gravitational force and gravitational potential energy. By definition, the gravitational potential energy is minus the integration of the gravitational force from infinity to the final position r. This is the potential energy at position r. So the U is defined by this formula. So it allows you to go from the gravitational force to the gravitational potential, okay, to the gravitational potential energy. And from the in the reverse direction, we also have another relation. The spatial derivative of the gravitational potential energy with minus sign will give you the force. So this formula will let you go back from U to F. Okay, now this part of the diagram we learned in chapter 5. Okay, now we consider everything in per unit mass. If I consider the gravitational potential energy per unit mass, I will have the gravitational potential. Okay, if I consider the gravitational force per unit mass, I will have the gravitational field strength G. Okay, but the gravitational field strength G is the same as acceleration due to gravity at that position. Okay, and the small g and the gravitational potential V, they are related exactly as in the same way as the gravitational force and the potential energy. If you replace U by V, if you replace F by G, then every of this equation will carry over. Okay, so this is nothing. The G and the V are nothing. We just consider everything without the small mass m or per unit mass m. Okay. Now, before going further, I would like to have a break here. It's already 20 past 3. So let's have a break of 10 minutes. And if you have any difficulty in following what I say, please feel free to raise a question by using the chat box, or you may simply unmute yourself. Okay. All right. Let's continue with our discussion. of a spherically symmetric mass distribution. Now, we already have mentioned that for spherical mass distribution, the gravitational force is exactly 1/r squared, right? As long as r is taken as a distance between the center. And we're not going to use a very general integration to prove that, but we are going to use the heuristic understanding of why this is so by using the concept of the field, okay, the concept of the gravitational field to let you have a heuristic understanding of why for spherical symmetric mass distribution, the forces go as 1/r squared. I think you already learned the concept of field in your high school study, okay? The gravitational field can be represented by the field lines. So imagine now I have a point mass here, and the effect of the gravitational field on the surrounding space can be represented by field lines, and the field lines are all converging to that point mass. Okay, so we draw lines from infinity converging to that point mass, and the distribution of the lines are symmetrical in all directions. Okay, so the distribution of the lines are even in all directions. Okay, because of spherical symmetry. And I draw an arrow which indicate the direction of the gravitational force. If I put a small point mass here, the direction of the arrow will then be the direction of the gravitational force. Okay, so what I have in mind is the following. Now, Faraday in the 19th century, the famous scientist Michael Faraday, who he discovered the law of electromagnetic induction. He actually used this picture to let him think about the field. He imagined the field lines is, for this case of a gravitational case, is originally from mass, and a larger mass will give more field lines. Okay, so you imagine if you double the mass here, it will attract twice as many field lines towards it. Okay, and the gravitational field strength at a certain position is the area density of the field lines. So it is field lines divided by the area. So the number of field lines per unit area represent the field strength there. Okay. Now it sounds quite abstract, but let us look at this picture. Now you see, I now have placed two small area. Now, although I haven't drawn it very small, but imagine they are very small area. Okay, so I now put two small area in a direct with the plane perpendicular to the direction of the field line. So the plane of this area will intercept the field lines. Okay, now one of the area is closer to the point mass. The other area is farther away from the point mass, and it is very evident to see that for the plane, for the area that is closer to the point mass, it intercepts more field lines. For example, I could say this area intercepts 4 field lines, and the farther area only intercepts 2 field lines. So if I calculate the field line density, which is the field lines number divided by the area, I will have a higher field line density here when I'm getting close to the point mass. And for the area that is farther away, the field line density will be less. Okay, so the field line density represents the gravitational field strength. If I'm closer, I get more field lines per unit area, so I get a larger gravitational field. If I'm farther away, I'm getting less field line per unit area, so I'm having a field with a lower in strength. Okay, so that's how we represent the field lines, the gravitational field strength. Now we can actually derive, so-called derive, not exactly derive, but we can actually have a heuristic understanding of why the gravitational field strength is inversely proportional to 1/r squared. Okay, essentially the gravitational force is proportional to 1/r squared. So let's understand why from the point of view of the field lines. Now we consider a distance small r from the point mass. Okay, so at this distance, I draw a large sphere. I draw a large spherical shell center at the point mass. So you imagine that this dotted line is a very large spherical shell enclosing the point mass at its center. So the very large sphere now intercept the field lines coming into it. Okay, and if we are going to find the gravitational field strength here, I have to find the total number of field lines intercepting this spherical surface and divided by the area. And the area I said is actually the area of the spherical surface, right? As the area of a spherical surface of radius r. Okay, and that's of course given by 4 pi r squared. This is the area of the surface of a sphere. Okay, and as I say, the number of field lines, I don't know how to calculate that exact number, but I know that the number of field lines is proportional to the mass m. If I have a larger mass m at the center, I will have more field lines coming in. Okay, so the number of field lines is proportional to m, and the area at radius r is 4 pi r squared. So this quantity, you can see immediately now, this quantity is proportional to the mass divided by r squared. And in SI unit, if you choose SI unit, I would say the gravitational constant G is the proportional constant. And so the formula will become Gm over r squared with a minus sign. Okay, so that is the idea. If you use this picture to understand the field, then you can naturally arrive at a conclusion that the gravitational intensity or gravitational field strength is inversely proportional to the square of the distance. Okay, because it's come with the area density of the field lines, and the area goes as 1 over r squared when you are getting further away. Okay. So there's a heuristic understanding of Newton's laws of universal gravitation. And apart from a factor of small m, this is just the Newton's law of gravitational force. Now I consider an interesting thing. Instead of having a point mass at a coordinate origin, now I imagine the mass to be distributed on a spherical shell. Now, by a spherical shell, I mean a spherical surface with negligible thickness. So it is hollow inside. There's nothing inside. And all the masses are now concentrated on the surface of a sphere. Okay. And I consider that the mass of this spherical surface, this spherical shell, to be the same as the original point mass. So I would like to ask a question. What will then be the field line distribution inside the shell and outside the shell? I would like to ask this question. Now I would argue that inside the shell, I would have no gravitational field. Okay. Now why I have this assertion? Why I can draw this conclusion? Now, because of spherical symmetry, because the mass distribution is still have the spherical symmetry, it will not be more on one side and less on the other side. The field is symmetrically in all angle. It would be the same at all angle. Okay, so the field lines due to this spherical shell will be even in all direction. Okay, so either it converges to the center or it diverges from the center like this. So it may be something like this, or either something like this or something like this. Okay, and it should be even in all direction. And suppose now I suppose it is like this. I suppose now I now have have a distribution like this, a few lines like this, I cannot have an angle for this field line. They must be converging or either converging or divergent because of a symmetry. I cannot break the symmetry of a sphere, right? But if consider like a field pattern like this, all the field line will be converging to a point at the center, right? But that means there is a point mass there, right? Otherwise, that would not be converging to a point, right? But that is not the case. I do not have a point mass here. This is the case of the point mass. But now the shell is empty, which means that I do not have a point mass at the center. So it is not logical to say that all the field line will be converging to the center. That's not possible. And similarly, that's also not possible for the field line to be diverging out. Because I saw that as far as I know, as a property of gravitational force, there's nothing that can give out the gravitational field line from a point, right? So these two cases are not possible. And so my only conclusion is that nothing is here. I cannot have another conclusion. The only conclusion is that I do not have any field lines inside the shell. And so inside the shell, what I would have is a zero gravitational field. The G or the force F would be 0. I do not have any field inside. That is the only possible conclusion. So how about outside? The field will also be what? Will also be symmetrical, spherically symmetric. It will be converging to the spherical shell also, just like the point mass. And because the mass of the shell is the same as the point mass, the number of field lines converging to the spherical surface will be the same as the number of field lines converging to this point mass. They will be the same. And so what I conclude is that the field outside a spherical shell will exactly be the same as a field due to a point mass located at its center. They are indistinguishable. Okay, if you place a small mass here and ask what gravitational force it experiences, it will just be the same as if you've placed the gravitational point mass. You've placed the point mass here for the point mass cases. They will be just experience the same force. Okay, so the field outside is indistinguishable from that of a point mass. So it will exactly be GM over R squared. Okay, so that is what we call the, I have a name for it. It is called the shell theorem. The shell theorem says that inside a spherical shell, the field is exactly 0. And outside the spherical shell, the field is exactly the same as if all the mass of the shell is concentrated at the center, just like a point mass. Okay. Now I have another proof of the fact that the force inside the shell is exactly 0. Now this is actually taken from Newton's book of Principia. Newton actually has this proof in his book. Okay, now this is a spherical shell. Now I consider a general point inside the shell. And I draw 2 small cones. You consider ice cream cone extending outward in the opposite direction. But I consider the angle of the cone to be very small. Can you imagine an ice cream cone like this? We imagine an ice cream cone like this with a very small angle. Okay, so I assume that this angle, assume that these 2 angles are the same, such that there are 2 ice cream cones diverging out in the opposite direction. And the first ice cream cone intercepts an area A1 on the shell, while the other cone on the opposite side intercepts another area A2 on the shell. And the distance between this point from A1 and A2 are R1 and R2 respectively. Okay. So let me ask a question. How much mass are there on these two areas? The masses on these two areas, M1 and M2, must be proportional to the area itself. So M1 over M2 is just A1 over A2. Because the mass is uniformly distributed on a shell, so the mass is simply proportional to area. You have a larger area, then you have a larger mass, right? So it must be proportional to A. But since this is a cone, right? These two cones are similar in shape. They are similar triangle. So that means if you have a larger area, you have larger heights, and the height is R. And the area of the base is proportional to the square of the distance of the base from the vertex. It's proportional to the square of the height of the cone. So A1 over A2 is R1 squared over R2 squared. Okay, because the area is proportional to the radius squared. Okay. Now, if you look at this equation and we arrange it, you will find that M1 over R1 squared is equal to M2 over R2 squared. But M1 over R1 squared is exactly the gravitational force produced by this area on this at this point. And M2 over R2 squared is exactly the gravitational force produced by the other pieces again at this point. But the two forces are in opposite direction and they are equal, so they cancel. And if you form a summation of all the opposite pair, if you consider the whole shell to be divided into many, many such pairs, then the gravitational force of each pair cancel, and so the summation of all the forces will be canceled. Okay, and so the resultant force will be zero. And so that's why there's no gravitational force inside a uniform spherical shell. Okay. So this is an important result we reach. If you have a spherical shell, then inside the shell, the G is exactly zero. The gravitational field inside the uniform thin uniform spherical shell is exactly zero. Okay, and for outside, small r larger than big R, the radius of the shell, the gravitational force outside is the same as if all the mass is located at the center, just like a point mass gravitational field. So you simply take the formula Gm over R squared, just like what you have for a point mass field. Okay, so that's an important theorem. Now, how about the potential energy? Now let's take a look at the field strength, the G first. The G is inversely proportional R squared outside and it's negative. So it goes like this. Okay, it's negative in value and degrees, the magnitude degrees as 1 over R squared. So it become like this. And inside the shell, the G is 0. Okay. Now, how about the potential? The potential is an integration of the field strength from infinity to R, and it becomes minus Gm over R outside. It is inversely proportional to R, so it decays slower, and also negative. So it goes like this. Okay. And inside the shell, the gravitational potential is a constant because there's no force inside. Now, if you integrate from infinity to the surface of the shell, you got this potential. But if you integrate further inward, because the field is 0, you do not get any extra contribution. And so the potential inside the shell is constant. It's a constant. It's the same everywhere inside the shell. So you have this horizontal line, which means that the gravitational potential takes the same value at every point inside the shell. Okay. So here are the distribution. Okay. Now, an important consequence of this theorem is the following. Suppose there's a point mass M and a spherical mass distribution. The spherical mass distribution isn't need not be empty. It may be a solid. Okay, now the inside may be filled up with a lot of mass. The distribution may either be uniform or even non-uniform. As long as the inside is filled up with mass, it's okay. And the mass distribution is symmetrical. There will not be more mass on one side and less mass on the other side. So let's imagine now you have a spherical symmetric solid mass distribution. And on the outside of this distribution, you have a point mass M at a distance r from its center. Now the spherical solid mass can now be divided into many thin shells. And for each thin shell, the force between that shell and the small mass outside is exactly GMM over R squared, right? So the sum of all the shell together will produce the same force. It's still GMM over R squared because R doesn't change. The R is the distance between the mass and the center. And this distance is common for all the shell. So if I form a sum of all the forces between the shell and the mass, I will get an expression that is exactly GMM over R squared. And that is Newton's result. Newton's found that for a spherical symmetric mass distribution, the force between the point mass and that distribution is exactly GMM over R squared, as long as R is taken as a distance between the center and the point mass outside. Okay, so I can imagine all the mass there to be concentrated as an equilibrium point mass M, and the force is exactly given by this. Okay, and that holds even if the density depends on R. Now, as long as the density is does not depend on angle, it only depends on R. This argument will still apply. Okay. Now let us use the important theorem that we have derived to calculate the gravitational force between a uniform solid sphere and a small mass, small m, that is located at a distance small r from the center of the sphere. Now the green thing, I draw it green deliberately because I want to emphasize that now the whole sphere is filled with a uniform mass distribution. Okay, so you imagine that there are a lot of masses here, and they are uniformly distributed inside the sphere. And now I pick a small point mass at a distance small r from the center. Okay, this small r is smaller than the radius of the sphere. The radius of the sphere is big R. How do I calculate the attraction force between this small mass and the large sphere? How do I calculate it? Well, I can divide the contribution of the force into two parts. I draw a spherical shell. The dotted line is a spherical shell of radius small r. If I extract the mass inside the spherical shell, I will have this spherical mass distribution of radius small r. For this distribution, the point mass m is outside, right? It's outside the sphere. So the gravitational force between m and this spherical mass distribution is exactly the same as if all the mass is concentrated at the center. So I can use the standard GMM over small r squared formula to find the contribution of this green part. And how about the outside? For the outside, I have a spherical shell like this, right? And I can see that the point mass is now inside the shell, is in the cavity. And from my previous discussion, I know that the gravitational field inside the spherical shell is exactly 0. I don't need to consider it. So this part does not contribute, right? So only the mass that is enclosed by the spherical shell will contribute to the gravitational force. And here I do the calculation. The yellow part does not contribute. The green part does contribute. And that is, I want to find the mass m prime, which is enclosed by the dashed line, the green part. So I find it by the volume ratio. If the total mass of the sphere is m, then I calculate the volume of the small sphere, which is 4/3 pi small r cubed, divided by 4 over p big R cube, which is the total volume of the sphere, multiplied by m, I got the m prime. I got the mass inside. And this is, of course, small r cube divided by big R cube multiplied by m. And the gravitational force will then be Gm prime. The m prime is this part, multiplied by small m divided by r squared. Now I plug in this m prime. So it becomes like this. The r cube cancel with the r, 2 of the r cancel with the r squared in the denominator. So I get only 1 r. And the final force is given by minus gmm r, small r, divided by big R cube. Okay, so now I find the force inside the spherical solid sphere. Now here is the a graph illustrate the force versus distance. When I am outside the sphere, the solid sphere, the force is exactly 1 over r squared, just like upon mass at the center. So it's simply 1 over r squared dependence as a point mass. And inside the sphere, a very peculiar dependence here. The force is proportional to the distance from the center. So it's a straight line because the slope is negative. So it's a straight line going down. Okay. And the two expressions agree with each other at the boundary, at the surface of the sphere. And that value is GMM over capital R squared. Okay. Now you can find the potential energy by doing this integration. If you want to find the potential outside, you integrate it through a point out the outside. But if you want to find a potential inside, you have to integrate all the way from infinity to this position, to the position inside. And during the integration, you must be careful because the expression of the force F are different at the two different regions. The expression of the force outside is 1 over r squared, while the expression of the force inside is r. So you have to separate the integration into 2 parts in order to find the correct answer. I would not do the calculation here. I don't want to confuse you further. I just state that you can find the potential energy easily, not difficult by using a direct integration. But you has to be especially difficult, especially careful if you want to find the potential energy inside, because you have to use 2 different expressions for the force. Now we have a small cast work. Okay, suppose we have a fixed shell. The green part is filled with mass, but the shell has a cavity inside, has a spherical cavity inside. The radius of the outer radius of the shell is capital R, and the radius of the cavity inside the shell is r over 2, and the total mass of this object is m. Now I want you to write down the expression of the gravitational force of a small point mass between a small point mass and this object. Okay, and for each of the case, you have to consider the small point mass is lying outside, the small point mass is lying inside, and small point mass is lying somewhere inside the material of the shell. Okay, and assume that for in this situation, assume that this. Sorry, I do not draw it very well. And when I consider the mass to be inside the matter, I let this radius. Sorry. Okay, get rid of this. I consider this radius to be small r. Okay, can you find out the answer? Now you just apply the shell theorem. For outside, the force is gm over r squared, right? For inside, the force is 0. The difficult part is when the mass is lying here. You have to divide the whole shell into 2 parts, right? The inside part contribute. You consider the mass of the inside. Inside is this dotted line, and it looks like all the mass is concentrated at the center. The outer part does not contribute. Okay, can you write down the mass inside first and find the force between the small mass and the mass inside? That would be the expression of the force here. Now you don't need to do every step. You just need to do the basic thing. If you write the formula correct, that is okay. You don't need to calculate all the way to the answer. Anybody knows what is the mass enclosed by this dotted line? Can you let me know? Now, first of all, what's the density of this object? The density is the total mass divided by the volume, right? But you have cavity inside, right? So you have to be careful when calculating the density. Okay. Now let's do it together. The density of the object is the mass divided by the volume of the object. But I mean, what I mean by volume is the volume actually occupied by the matter, right? So it's a difference between the volume of the two spheres. The large sphere having a volume of 4/3 pi r cubed, while the cavity is having a volume of 4/3 pi r/2 cubed, right? So the large spherical volume minus the volume of the cavity will give you what? Will give you the density. Is that right? And there's no harm in picking out the constant. Okay, I can pick out all the constant here. So this become what? This become 1/1 minus 1/8, right? Because it's 1/2 cube, right? And that become what? That become 1 minus 1/2 is what? 1/8 is 7/8, so it's 8/7. Okay, we got this value. Okay, and the volume, the mass inside, which is indicated here, the mass I call R prime. The M prime is a function of R because different radius will have different mass enclosed. So I let it a function of R will be equal to what? The volume of this part, which is 3/pi R cubed. The speed of radius small r minus the volume of the cavity. The volume of the cavity is pi r over big alpha 2 cube, right? So I would have what? I would have this. Sorry, I should multiply by rho. I missed a factor of rho. The volume multiplied by the density will become the mass, right? Is that right? So I now have what? I'll have 4. Let me extract a factor of this. And so in the bracket, I have small r cube over big R cube. And here I have a factor of 1/8. And the density is what? Density is this guy, right? So I have this one inserted here. And this factor exactly cancel this factor except for M, right? And the M doesn't cancel, sorry. Right? So what I got is the following. So this is the answer I got, multiplied by M, right? So the force will then be what? I do not have enough space. I hope you can see it. Gm prime, small m over R square. Okay, because all the mass seems to be concentrated at the center. So when you divide this expression by small r square, you add a small m by g and you got the answer. And the answer will be right here, right? Sorry. Given by what? Given by g. Let me add the minus sign. Now I have gm after divide by like this. Okay. So this is the answer. Okay. I hope I do it correctly. I might have mixed a careless mistake. If you find some careless mistake, please point out. Now, everybody knows the gravitational field strength or the gravitational acceleration near the surface of the Earth is about, on average, 9.81 meter per second square. But we can actually derive it from Newton's law of universal gravitation, assuming that the Earth is a perfect sphere. Now, the Earth is actually not a perfect sphere. The Earth is have a small bulges on the equator, and so at the equator, the radius of the Earth is larger than the radius along the pole. Therefore, at the first approximation, let us assume that the Earth is a perfect sphere. So for a perfect sphere of mass m and radius r, if I place a small mass on the surface, the gravitational force is GMM over big R squared. And this is, of course, equal to the weights of the body. The weight of the body on the Earth's surface, mg0, where g0 is the acceleration due to gravity on the Earth's surface. Okay, so I use g0 to denote the acceleration due to gravity because I'm going to have an extension of the value of g that goes beyond the Earth. So let me use the naught to denote the gravity acceleration at exactly the Earth's surface. Okay. So after canceling the m, I find the value of g0, and I only have to insert the value of the g, the gravitational constant, the mass of the Earth, and the radius of the Earth. And after I insert all this value, I get 9.81 meters per second squared, which is the average value of the gravitational field strength or acceleration due to gravity on the surface of the Earth. Okay. Now let's consider some variation due to the rotation of the Earth. Now for simplicity, I only consider a mass placed on the equator because I don't want to handle the angle. I only want to show you the essential idea. So I now consider a mass placed on the equator of the Earth. So it rotates together with the Earth with an angular velocity omega. Okay, the angular velocity is of course due to the Earth's self-rotation. Okay, now due to the rotation, I have to distinguish between two weights. mg is the true weight. Okay, mg is the gravitational force due to the Earth acting on this mass. So it is the true gravitational force. Okay, so it's a true weight of the object. And the normal reaction is the reaction force due to the ground or due to the any surface on the Earth on this object. Okay, it is a supporting force, the force that supports the object. So it is direct vertically upwards. I call this non-reaction force N. Now, why are N and mg not equal if the body is at rest on Earth, right? The body is now placed on the equator. So why are the two forces different? The two forces are different because the body is now rotating together with the Earth about this axis. You have the daily rotation of the Earth. And so this body is now undergoing uniform circular motion. If you have uniform circular motion, that means there should be a net force. What provides the net force? Well, the difference between N and mg will provide the net force. mg has to be slightly larger than N in order to provide a net inward force. And that net inward force is a centripetal force of the circular motion. Okay, so I have mg minus N, the net force, the net inward force, to be equal to m big R omega squared, where omega is, of course, the angular velocity due to the rotation of the Earth. And so I can solve for m. M is small m multiplied by g minus R omega squared. So effectively, you can see if I measure the apparent weight of the object, now this is the normal force is actually is the weight of the object, the apparent weight of the object. If you place a electronic balance, if you place the object on the electronic balance, this is the weight that you measure. Because the electronic balance only measures the normal force acting on the object, it cannot measure the actual gravitational force. What it can measure is the supporting force is exerted on the object, right? So the apparent weights that the electronic balance measure is N. Okay. Now, so N is equal to M multiplied by this guy. But this guy is what? G minus r omega squared. So you have the graph, effectively, you have the gravitational acceleration reduced by a factor of, by a amount of r omega squared. So there's a change in G, there's an apparent change in G, which I call delta G. And that's given by minus r omega squared. If I plug in the value of r for Earth, the radius of Earth, and I calculate the angular speed of rotation of the Earth by dividing 2 pi by the period of the Earth. The period of the Earth is a day. A day is 24 hours, and 1 hour has 3,600 seconds. So this is a total number of seconds in a day. 2 pi divided by total number of seconds in a day is the omega. So I have omega squared here. And what I find is delta G is equal to 0.034 meter per second squared. And when I compare this value with the gravitational acceleration 9.81, I find that this is only 0.34%. So this is a very small effect, but it's there. Okay, so if you measure the weight of the object on the equator, and you then measure it on the pole, you will find that if you measure on the equator, then you find that its weight will be less by 0.34% due to the rotation of the Earth. Okay. Now I better stop here. In the next lecture, we will discuss a little bit more about, for example, some concept you learned in high school, like, for example, escape velocity, the minimum velocity that allows you to escape forever from the gravitational force of Earth. And also, I will discuss with you the circular motion under gravity. This is just a review you already learned in high school. And eventually, we will go to a deeper discussion on planetary motion, and that is with the elliptical orbit. Now, we will not go into the elliptic orbit in detail because the mathematics is very complicated, but we will highlight several important consequences if the orbits of the planet is elliptical. We will qualitatively discuss those consequences and how to calculate the energy and how to calculate the velocity of an object in an elliptical path. That's what we are going to do in the next lecture. And I hope you enjoy the weekend, and let's stop